So we're going to continue on with thermochemistry, and we're starting off with heats of reaction. We talked a bit about them before, but what actually goes on? Why are some reactions exothermic and why are some endothermic? Well, most of it's due to the energy that's required to break the bonds and the energy that's released when the bonds are formed. For example, in the example of hydrogen gas and chlorine gas turning into hydrogen chloride gas, it has a negative enthalpy change, which means that it's an exothermic reaction. Let's have a look at the various bonds that are broken. You have hydrogen bonds that are broken and you have chlorine bonds that are broken. So energy is absorbed when those bonds are broken, which means that it's positive. So you have positive amounts of enthalpy. Lots of hydrogen, a smaller amount for the chlorine. But that energy is released when you form hydrogen chloride bonds, and you get minus 433 kilojoules per mole of hydrogen chloride. So for the reaction of 1 mole of hydrogen and 1 mole of chlorine, we've got a net reaction of our bonds broken minus our bonds formed. Well, bonds broken plus bonds formed, which gives us this heat of reaction, minus 185 kilojoules. So you notice that this is not kilojoules per mole. If we wanted to do it per mole of hydrogen chloride that was formed, we'd then have to divide it by 2, because in this reaction, 2 hydrogen chloride gases were formed. So the enthalpy of reaction is, this enthalpy is actually to do with the enthalpy of the reactants in this case, which is 1 mole, 1 mole. If we wanted to actually do it in terms of the products, we would have to divide this by 2, and then it would be in terms of 1 mole of hydrogen chloride gas formed. The bond energy is this energy that is absorbed or released when a covalent bond is formed, absorbed when it's broken. It's always positive because the energy is released when the bonds are formed. So it's kind of like thinking about the energy, potential energy that's in the bonds, and when you break that bond, the energy is released. But it's really not a component of the molecule's potential energy. So you think of the energy in there, but it's actually really the energy that's required to break a bond. You can estimate the enthalpy of reaction from bond energies simply by looking at the sum of the bond energies that are broken and the sum of the bond energies formed, and taking those that are taken away and those that are broken. So it's basically saying, I break something up and I add them together, what's left over? That's the energy of the reaction. An example that's here is for methane, combustion of methane in oxygen. You can see that we have 4 CHs. I tend to use the organic chem representation, so you can sit there and go, oh, yep, that's 1, 2, 3, 4 CH bonds. We're going to have 4 hydrogen and 4 oxygen. So we're going to produce them all into atoms, and then we're going to turn them into carbon dioxide and water, which means we have 4 OH bonds and 2 C double bond O's. Now it's very important that you remember the difference between double bonds and single bonds when you're looking at these. So you might need to actually draw those diagrams, because a CO is different from a C double bond O in terms of bond energy. We can calculate the bond energies broken and those formed simply by adding up these bond energies. Normally you get a table. So first we've got 4 carbon-hydrogen bonds, so that's 4 times 99, and then we've got 2 oxygen bonds, double bonds, which is 199. And then we have 4 lots of oxygen-hydrogen bonds, that's the water, and 2 lots of 192, which is the double bond C, so O double bond C in the carbon dioxide, which gives you minus 184 kilocalories per mole. You can see I've messed up there. But this is in calories. 1 calorie is equivalent to about 4.18 joules, but the Americans use calories a lot more often than they use joules, even though joules is the standard unit. Most of the time we'll be using joules, but this example that I got from the net was in calories. The other thing that you can do, although you can use the bond energies to estimate enthalpy of reaction, this one's actually not that correct, because if you want to compare this reaction to the standard enthalpy of the reaction, you need to include a correction factor for converting this hydrogen gas into water. So you need to include the heat of condensation, or the heat of vaporization of 2 moles of water, which was 10.5 kilocalories mole. So when we include that in, we get minus 250 15 kilocalories per mole of reactant. What is the standard state? Well, if we want to compare between different reactions, we need to use a form of enthalpy which is defined as a standard state, when all the reactants and products are present in their standard state. For most of the time, this is the state that they're normally in, at atmospheric pressure and at room temperature. So pure substances like water would be liquid, but gases like oxygen and hydrogen are gases, obviously. Sometimes you might have a gaseous mixture, and the standard state of any component in the mixture is that component at 1 atmosphere. And often you might have a solution to an aqueous solution. In that case, the standard state is 1 mole per litre. Since the standard state can depend on its temperature, it's often listed as the standard enthalpy of formation, which is also called the heat of formation. This enthalpy of formation is the enthalpy of 1 mole of compound in its standard state formed from elements in their standard states. So you can see that the standard enthalpy of formation is actually a reaction, and you can set up a reaction to form any compound from elements in their standard states. You need to use the little degree and the F to note this standard enthalpy of formation. Sometimes this actually requires writing equations in a form so that only 1 mole of product is formed. So the example we have for water is that you're using hydrogen gas, which is in its standard state, oxygen, which is in its standard state, and liquid water, which is standard state. The formation for that is minus 68.3 kilojoules per mole. But we had to put in a half an oxygen just so that our equation actually had 1 mole of product. And in these cases, the enthalpy of formation is always designated for the product. One thing to note is that the enthalpy of formation of an element in its standard state is 0, and that's because you use the elements to form a compound. So the elements are 0, but the compound is not 0. So if you needed to calculate the enthalpy of a reaction from the enthalpy of formation, then you need to sum up all of the products and all of the reactants. And the enthalpy of the reaction is simply the sum of the products minus the sum of the reactants. Of course, when you do that, you have to take into account how many reactants there are. So if you have a certain number of moles, for example, A moles of A substance, then you need to include that in your calculation. It's a bit hard to look at it in this, but you can remember it in terms of an example. The example we have here is nitrogen dioxide, which is a gas formed from nitrous oxide and oxygen gas. We use the formula, and we need to know, first off, what are the standard states? They're all gases, which is easy. We have oxygen, which is 0 because it's an element. The enthalpies of formation for nitrous oxide is 90, and for nitrous dioxide is 33. So if we put these into our equation, we have on one side 90, on the other side 33. So you're going to have products minus reactants, 33 minus 2 times 90 because we have 2 of them here, and you end up with minus 147. So this reaction is exothermic. What is the difference between a bond energy and the standard enthalpy of formation? We looked at the bond energies, and they were basically measured from bonds breaking and forming. And they use a table of average bond energies. What I mean by average is that you might have a CH bond, and that's calculated from an average of a number of different molecules. So the difference between having a CH in a methane molecule, which only has CH bonds, and looking at a CH bond in ethanol would be a slight difference in that average bond energy, and yet we use that average. Because it's an average, it means that we're only estimating the enthalpy of reaction. And sometimes we need to include latent heat to convert to standard enthalpy so that we compare with the standard enthalpy of reactions. It's calculated by the bond energy broken and formed, and for your heat of formation, it's the products minus the reactants. You can see that here we've got products minus reactants, but here we've actually got broken and formed. Same sort of thing. Formed is really your product, reactant is really your broken. But because bond energies are always positive, we've put it in this form. Really, it's exactly the same equation. For a standard enthalpy of formation, all your components have to be in a standard state, which means that some reactions don't actually occur. They're ideal reactions. So these are theoretical calculations that can be used to estimate the heat of reaction for reactants that you might not actually see happen in real life. So the bond energy is used to calculate these heats of formation sometimes, and also the heat of formation standard heat of formation is used to calculate those heat of reactions. But in both cases, you can look at the heat of reaction. This is the sort of tables that you might get. You can see that there's standard enthalpy of formation there and bond energies there. And remember the average bond energies. You usually get one with single bonds and one with double bonds.